So he throws the ball away like this, and there's a hook. He has a hook as his arm, and the ball now is traveling with 5 meters per second. It's a fairly fast ball. Alright, so the big question here is what kind of impulse does Fred get, and in other means, other way to ask, what speed, what velocity will Fred gain? So let's put up the formula again. So that is the total momentum is m1 v1 plus m2 v2. Alright, so since the total momentum is conserved, we will set that equal to 0. Alright? Because they're moving in opposite direction. And then we can rearrange this to get, let's say that I'll just rename them slightly. So this will be M Fred V Fred, and this will be M ball V ball. Is equal to 0. So let's find out what Fred's velocity will be. Now first of all, we can move things over so that we get M Fred V Fred is equal to minus M ball V ball. Alright, so now we just divide, so we get V Fred is equal to minus M ball V ball divided by M Fred. And now we have it. We just have to plug in the numbers, and that will gain us 5 kilograms times 5 meters per second divided by 80 kilograms. Well, this is fairly easy to calculate together. The first part, that is 25 kilograms meter per second divided by 80 kilograms. Now I could probably calculate this in my head if I wanted to in a fairly long time, but because I'm pressed on time, I'll just use my good phone here, and because I'm lazy, to figure out that Fred's speed will become, that is a minus about that, minus 25 divided by 80. Alright, so here's the crucial thing. If Fred gets a velocity, then he'll move. If Fred doesn't get a velocity, Brian Mullin is correct, and it will never ever be possible for a space shuttle to nudge its direction around using these boosters, small boosters, and it will, for that matter, never ever be possible for anything in outer space to fly anywhere using impulse. That is an impulse engine that is not from Star Trek, but that will be a rocket engine or anything of the sorts. Anything where you generate a force going in one direction and then expect to get an opposite and equal size force in the other direction. As far as I remember, that is Newton's second law. But anyway, the result is that Fred, poor Fred, will get a velocity of, well, I can remember it's minus 0.31 meters per second. This is really crucial, because this clearly shows that Fred, when he tosses the ball in outer space in one direction, he'll begin to move in this direction will, with let's see, v Fred is equal to minus 0.31 meters per second. Now you have to remember here that this is just not an instantaneous little nudge he gets. He will continue to move in that direction until something else influences him. And the only thing that can influence him is his little jetpack. So hopefully Fred discovers this quickly and might possibly get enough time to boost himself towards the space shuttle. Now, I've of course fooled you a little bit here, because the thing is that as long as there are no external forces working on Fred, then the boost he gets from his rocket, or his booster, will keep him going in the same direction until something else influences him. So the real thing here is that this will only work if there's an external gravitational force nearby that can influence him. But it's just to get the idea that of course a space shuttle can move itself around by using these boosters or little nozzles that spray matter out. The principle goes just exactly the same. You have a space shuttle, not very pretty one, with nose here, cockpit up here, and the wings. And the same principle applies. We have the little nozzle down here. It will spray matter out in this direction, let's say with 50 meters per second. And this is of course a little more complicated because you have to assume a total mass, because it's not just one clump that is put up, it is small clumps. So you would actually have to integrate over time. But in any way, let's just assume that this is a fixed mass that is being sprayed out of 0.5 kilograms. And let's say that the space shuttle itself, that is V particle, M particle, oh sorry, mass of particle is equal to 0.5 kilograms, and let's say that the mass of the shuttle is equal to 10 tons. I don't know this, I'm just guessing what it could be. Now, you can of course say, you can sum it up and then just assume that this is a linear spray that's coming out. It's a constant force that is influencing it. But in any case, you have that the momentum is conserved, and that is why the space shuttle will gain, however small it is, a little nudge in this direction, which we'll call V shuttle. That is the same principle that applies. It will also work on Earth. In any physics textbooks, especially on a university level or college level, you will find many calculated examples of this. You can have, as I have here, a rifle and a bullet, where you have a rifle not a very pretty one, but anyway, that fires a bullet away. The bullet has a speed of, let's say, 300 meters per second. The mass is 0.0 kilograms. I think that would be around 300 grams or something like that. And the rifle itself, M rifle, has a mass of 3 kilograms. Again, you can use the same principle. You will have that M rifle, V rifle, would be equal to minus M bullet, V bullet. Now, sorry, B's. One thing you have to consider here: which direction are you going? Now, if we say that this is the positive x direction, then you would have that the bullet going this way would have to be positive, and that is why when I move it over on the other side, it will become negative. Now, I just assumed in all the examples I did here that the positive x direction is in this direction, because that's what I'm used to. But if you invert the positive x direction, and that might be useful in some cases, then you will have to remember when you do this calculation what is going in which direction. Alright, I think that concludes my video on my answer on the first video of Brian Mullin.